Hello, George Nonchik back again. In this video, I'm going to solve this simple unbalanced bridge problem. This problem was originally posed about a week ago by Professor Walter Lewin of MIT in a series of problems that he poses online. This is problem number 24. I have the link to the original video in the pinned comment on this video, as well as in that pinned comment you will find a index of the content and material in this video so that you can jump ahead or go to various topics that might be of more interest to you rather than having to view through the whole video. It's going to be a rather lengthy video because I'm going to solve this network many different ways, about 6 different ways using different techniques. I'm going to be using loop currents, mesh currents, node voltages, matrix methods, network reductions using Thevenin equivalent circuits, also network reductions involving Y delta conversions, or delta to Y conversion in this case, and flow graphs. And you can, in the pinned comment, look to where the timestamp is for any particular technique that you might be interested in if you don't want to watch the whole video. The first method I'm going to use is the most direct and simplest way to solve this network. Some of the other methods like mesh currents and node voltages are a more systematic approach that you would use for larger networks. On simple networks, a lot of times you can do things by inspection, like with this particular network. But when you're dealing with much larger networks, if you don't have a good bookkeeping method and a systematic approach, you can get really buggered up because of all the equations and variables that you're dealing with. But in this network, we don't. The easiest way to solve it, you only have 2 unknowns to solve for, and it's fairly easy to solve using other methods besides these high-powered techniques like node voltage analysis. I have the network drawn twice here to illustrate different loop currents that we can use to solve the network. Now, what I'm going to do is first show the designations of the unknowns that the video asked for a person to solve. One was, what is the current in the bridge resistor? Is it going upward or downward in this orientation? And what is its value? And what is the value of, say, capital I, which is the current being sourced by the voltage source into the network? And we'll call this current in the bridge resistor small I. Now, the most direct way to solve this network is to establish 2 loops. Now, when you do loop currents, you have to have as many loop currents as necessary to cover all the components in the network. You can't leave any of the components unmarked as far as a current flow goes through it. So I'm going to pick 2 loops. One loop, I'm going to go from the voltage source up around, through, and back this way. And I will call this current I3. I've also have some labels here on nodes. This is node A, which is the positive end of the voltage source, node B, which is the negative end, and then nodes Y and X on the bridge resistor. The other current that we're going to choose is going to be this loop, starting from the positive end of the voltage source, then going from node A to node X, then up and around. So we can see that with these 2 currents, we cover every component. We only need 2 loop currents to do that. And this current we will call I1. Now when you do loop currents, what you're using is Kirchhoff's voltage law. You go around a closed loop, and Kirchhoff's voltage law states that the sum of the voltages around a closed loop is equal to 0. So in loop 1, which is, I will call I1, and this is in loop 1, so this is loop going from A, X, Y, B. So we're going A, X, Y, B, and back. And in loop 2 will be for I3, and this will be loop A, Y, X, B. So we'll go A on up, Y, X, B. This is the green. So this is the green path, and this is our purple-violet path. All right, let's look at the first loop. Loop A, X, Y, B. So we sum all the voltages. I1 is going through 2R, so we write 2R I1 plus R times, now we have 2 currents flowing in R. The positive direction is in the direction of I1, so it's I1 minus I3, because you see I3 is in this direction and I1 is in this direction. So we have R times I1 minus I3, and then I1 is flowing through 2R, so we have plus 2R I1 and minus V equals 0. We're going through these 2 resistors. We come back to the minus terminal of the V. That's why we have minus V, and that's equal to 0. Let's gather like terms, so we'll have equation 1. Equation 1 will be V. Bring it off to the right hand side. We add the I1, so we have 2, 1, and 2, so we have 5 RI1, and we have a minus RI3. Now I'm going to divide through by R, so we will rewrite this equation as V over R is equal to 5I1 minus I3. Now, the next loop, I3, the green loop, we're summing our voltages. I3 is going through R, so we have R, I3. We're going down through the bridge resistor. We have 2 currents now. We have I3 minus I1 times R, or R times I3 minus I1. And then we go through the resistor. I3 is the only current there, so we write RI3. And we're back to the voltage source, so we have minus V, and that's equal to 0. Again, moving V over, and I'm going to divide through by R since it appears in each term, and we add our R3s. We have one I3, another I3, and another I3, so we have 3 I3s and a minus I1. So that's our second equation. This is equation 2. Now, we're going to do some simple manipulations here. I'm going to write down equation 1 and 2 here. So we've got 5I1 minus I3 equals V over R. This is equation 1. Equation 3 is, we line up our variables. So we have a minus I1 plus 3I3 is equal to V over R. So we can just do simple equation addition here. I'll carry this equation over. So we have 5I1 minus I3 equals V over R. I'm going to multiply this equation through by 5. So we have a minus 5I1 plus 15I3 equals 5V over R. Let's add the equations. The I1s go out. We have 15 minus 1, or 14, I3 is equal to 6V over R. We're simplifying, dividing through by 2. We have 7 I3 equals 3V over R. Or from this equation we get that I3 is 3V over 7R. So that's the solution for I3. Now likewise, what we'll do here is we'll carry the bottom equation through, minus I1 plus 3I3 equals V over R. And I'll multiply the top equation by 3 so that the I3s will cancel. So we have 15 I1 minus 3I3 equals 3V over R. Just multiplying this equation through by 3. We add the equations. The I3s go out. 15I1 minus I1 is 14. I1 is equal 3 plus 1, or 4, V over R. Dividing through by 2, we get 7I1 equals 2V over R, or I1 equals 2V over 7R. So now we have the solutions that we need. What is I? Well, I is, let's choose the current as being positive upward. If we choose it to be positive upward, then I is equal to I1 minus I3. Well, our I1 is 2V over 7R, and our I3 is 3V over 7R. And so we end up with a minus V over 7R, which tells us the current is actually in the opposite direction of what we chose. I chose it to be positive upward, but it actually comes out negative, which tells us it's going downward. It's actually the current of I3 minus I1 in the positive direction. So the magnitude of I is V over 7R. How about capital I? Well, capital I we see is I1 plus I3. So cap I equals I1 plus I3. So that's 2V over 7R plus 3V over 7R, or 5V over 7R. So that's the current coming out of the voltage source into the network. So the network's solved. There it is. Here are the answers. Now, I'm going to show another way using picking different loop currents for solving the network. I'll just let you look at that a second. Get that before I erase it. Okay, again, we're going to use Kirchhoff's voltage law around loops, but we're going to choose different loops this time. I'll now solve the network using a different set of loop currents. As before, we have our little I current going through the bridge resistor, and I'm choosing downward as the positive direction. And I'm going to choose 2 loops going from the voltage source. The first one will be going in this inner loop, and I'll call this current I1. And then the other current will be going through the outer loop back to the battery, and we'll call this current I3. Now we can see here that the sum of I1 and I3 is the current cap I being sourced out of the voltage source into the network. That's also another current that we're looking for. So I'll just write that down here, that we have cap I equals I1 plus I3. And we're also looking for little I. Now what we do is, again, we'll use Kirchhoff's voltage law around loops and sum the voltages. And by the Kirchhoff's voltage law, we'll go first around the outer loop and then the inner loop. Since they both sum to V, we can equate the equation. So I'll just do that directly. Going around the inner loop, we have 2R with current I1 flowing through it. So V is equal to 2R I1, and then I1 is flowing through resistor R here, but we also have another current flowing. I is joining I1, so we'll put in currents here. The current flowing in this resistor is going to be I plus I1. The current flowing in this resistor is I1. The current in this resistor is I3. And I3 less I1 is flowing in this resistor, so we'll call this I3 minus I1. So now we have all our currents in terms of our unknowns. So now, again, summing the voltages around this loop, V is equal to 2R times I1 plus R times I plus I1. Gathering like terms here, we can write this as 2RI1 plus RI1, or 3RI1 plus RI. And this is also equal to the voltage around the outer loop. Summing the voltages, V is equal to I3 times R, or R I3 plus I3 minus I going through the 2R resistor. And combining like terms here, we have an R I3, 2R I3, so that's 3R I3 and minus 2R I. We can equate both equations here. So we have 3R I1 plus R I is equal to 3R I2 for I3 minus 2R I. That's all right there. Now we can cancel out our R's, and we notice that we have a 3I1 plus I is equal to 3I3 minus 2I, or we have 3I1 plus 3I equals 3I3. Canceling out our 3's, we get I1 plus I is equal to I3. We'll call this our equation 1. And if we rearrange and write it as I3 minus I is equal to I1, call that equation 2. Now what this tells us is that we have symmetry in the network. I1 plus I is equal to I3. I1 plus I is this current, and this is equal to I3. We have I3 here, so this is I3. Also, I1 plus, or I3 minus I is equal to I1. I3 minus I, that's this current, and this is I1, which is this current here. So we see that this statement tells us that the currents across the arms in the same resistors have the same current. And we'll be using that symmetry fact here. Now, let's sum the voltage along the path going from the voltage source around node A to Y down through the bridge resistor to X and over to B. And we'll use our current symmetry. So V is equal to Ri3, that's this one here, voltage, and now we get the voltage here, which is Ri, and then the voltage across here, which is Ri3. Or we have 2Ri3 plus R2 or Ri, and dividing through by V, we have V over R. V over R equals 2I3 plus I. We'll call this equation 3. Now, on the outer loop, going from A, Y, B, we can sum our voltages. We've already done that on the outer loop here, but we'll do it using our current symmetry now. So we can write that on the outer loop, V is equal to I3R plus I1 R2. So we have R I3 plus 2R I1. Or rewriting this, dividing through by R, we have V over R equals I3 plus 2I1. And this is our equation 4. Now, we have everything we need. All we have to do is combine equations properly, and we can solve the network. So we have our equations. Let's see here. Okay. So here's our equations. We have equation 4, equation 2, equation 1, and equation 3. Now, let's equate equation 3 and equation 4. So we have V over R is equal, equation 3 is 2I3 plus I, and that is equal to equation 4, which is I3 plus 2I1. Combining terms, we get I3 plus I1, or I3 plus I is equal to 2I1. And we will call this equation 5. Now, to equation 5, let's add equation 2. So equation 2 is I3 minus I is equal to I1. This is equation 2. let's combine them. We get 2I3 equals 3I1. So now we have a relationship between I3 and I1. Call this equation 6. Now, from equation 2, let's double equation 2. So we'll write equation 2 as 2I3 minus 2I equals 2I1. Now we can substitute in for 2I3 from equation 6. So we have 3I1 for 2I3 minus 2I equals 2I1. Combining, bringing the 2I1 to the left and 2I over, we end up with I1 equals 2I. So now we have a relationship of I, what we're looking for in terms of I1. This is equation, let's say 7. And we got our equation 6. Okay, now let's substitute into equation 1, equation 7 for I1. We can eliminate the I1 and get I3 in terms of I also. So from equation 1, we have I3 is equal to I1, which is 2I plus I, or 3I. This is equation 8. Now, we're almost home. I'll get rid of this right here. Now notice that cap I is I1 plus I3. And we can write that now in terms of equation, in terms of I. I1 in equation 7 is 2I. And equation 8 gives us I3 in terms of I. So that's 3I. So, capital I, the current coming out of the voltage source, is 5 times the current in the bridge resistor. Now, let's substitute equation 8 into equation 3. Get back here. So we're going to substitute in for I3 in terms of I, and we can solve for I. So we have B over R is equal to twice I3. Well, I3 in terms of I is 3I. And to that we add I. Or we end up with 7I. So we're done. We can solve for I now. I is equal to V over 7R. That is the answer. And since we have I, we get cap I. Capital I is 5 times I, or 5V over 7R. So there's the answers. A lot longer than the first method, but it shows that as long as you do everything correctly, all roads lead to Rome. You get the same answer. The answers are unique. Now, what we've done is the first time we chose 2 loop currents that went through all the resistors, and the answer fell out rather quickly. This one, we chose loops a little differently, and it took a little longer to get to the answer. And this is generally what happens with networks, where experience comes in, is to recognize the shortcuts and the best way to choose your loop currents so as to make the work easy. Now I'm going to use what's called a Thevenin equivalent circuit to reduce the network to allow us to solve for the current I in the bridge resistor. Now, just for variety, I've changed the orientation of the current I as positive is going from node X to Y. I've redrawn the circuit, I've flipped it 90 degrees. You'll see in a moment why that makes sense to do it in this case. It'll be easier to see what I'm doing. Now, a Thevenin equivalent tells us that if I break the circuit at any point in the network, no matter how complex, and I look back into the network, I can represent it with a single voltage source in series with a resistance. We call the voltage on that voltage source the Thevenin voltage, and the resistance looking back into the network as the Thevenin resistance, or the Thevenin impedance. So if I break the circuit at this point and look back into the network from node X, I'm going to see basically a Thevenin voltage source in series with a Thevenin resistance. I'll call that RTH and VTH. And this will be at node X. Looking back into the network, that's what I'm going to see. And the same thing looking back into node Y. If I look back into node Y, I'm going to also see a Thevenin voltage source and resistance, but they might not be the same. I'll call this VTHX, RTHX. This will be RTHY and VTHY. We need to solve for those. Well, the way we can do that is to better see what's going on. I can take and put an identical voltage source on this side. Call it V. I haven't changed the network at all. We have two voltage sources in parallel of the same value. That means no current will flow here, and I can break the network. So doing so, I can do, the network will look like this. Well, actually, we can just keep that connection there. So what I have looking in here is a voltage source working into a voltage divider. This is V, this is 2R, this is R, and this is my node X. So looking in, the way we get the Thevenin voltage is the open circuit voltage with no load connected here. Well, that's just a simple voltage divider. VTHX then is the open circuit voltage as we see here, so it will be R over R plus 2R, the voltage divider equation, times V. Or VTHX is just going to be V over 3. The Thevenin impedance looking in is the resistance we see when we replace all independent sources with their internal impedance. In that case, an ideal voltage source, its internal impedance is a short. So looking back into this network, what we have with the voltage source shorted, and looking in here, we just have R in parallel with 2R. Well, what it looks like is we have this combination. This is my RTH, this is 2R, and this is R. That resistance, we could the resistance looking in will just be R over 3. Parallel resistances is R times 2R times R over 2R plus R. So this is 2R squared over 3R, oh, I'm sorry, it's 2/3 R. So the Thevenin resistance looking in is just 2/3 R. So I can now replace, redraw this. So for this part of the network, my VTH is just V over 3, and my RTH is 2R over 3. That's at X. Now, looking in Y, we do the same thing. The voltage, open circuit voltage looking in here is just the voltage divider flipped around. And we have the R on top and the 2R on bottom. So I'll just look at that one. This is our connection at Y. So that becomes R on top and 2R on bottom. And this is the Y connection. So the VTHY will just be 2R over R plus 2R times V, or 2V over 3. So this voltage here, VTHY, is 2V over 3. How about the Thevenin resistance looking in? Well, we replace the voltage source with its internal short, so we have just what we had before, an R in parallel with 2R, so it's going to have the same value for the Thevenin resistance. So there's our Thevenin equivalent network, and now we attach our bridge resistor. So as far as this bridge resistor is concerned, it cannot tell the difference between this network and this network. So the current flowing in it will be the same I as in the original network. But this network is very simple to solve. We have a series network. So summing voltages around the loop, starting here, our current I goes through 2/3 R, so we have I times 2R over 3, that's the voltage here, plus RI, plus I going through 2R over 3, and we're going in the positive sense on this Thevenin source, so that's plus V, 2/3 V, and then we're coming in on the negative side here, so that's minus V over 3, and that's all equal to 0. So simplifying the equation, we can gather I, so we have 2/3 and 2/3, or 4R over 3 plus R for I, and plus 2V minus V over 3 is just V over 3, and that's equal to 0. So combining here, this is I times R plus 4/3 R is 7R over 3. And then we bring the voltage on the other side, and we can solve for I. I is negative V over 3 divided by 7R on 3. The 3's cancel, so it's minus V over 7R. That's our current I. What this is, the minus sign is telling us is I picked the wrong direction, that the I is actually going from the Y terminal to the X terminal. It's actually going in this direction with the value of V over 7R. And that's what we had before. Now, of course, once we have that, then we can solve for the other currents in the network like we did before to get what the total current is coming out of each of the sources. Now, when you do these substitutions and do accomplish network reduction using Thevenin equivalent, the only information that you can get related to the network is between the terminals, outside the Thevenin network. You lose the network information during the transformation. In this transformation here, I cannot determine what any of the currents are in the R or 2R resistors. I can only determine what the current is in the bridge resistor, because we've lost that information on the rest of the network when I've done the transformation. But the Thevenin network's equivalents are very, very powerful. It doesn't matter how complicated your circuit is, whether it's an AC circuit involving resistors, capacitors, active circuits with transistors, operational amplifiers. You can always break a circuit someplace and look back into a circuit and find its Thevenin equivalent and simplify the analysis if you don't, if all you're worried about is focused on a particular voltage or current like we were here. We can greatly reduce the analysis complication by breaking a network, get the open circuit voltage, then kill all the sources and get the Thevenin impedance. The other way you can do it is, it turns out that the Thevenin impedance is the ratio, RTH is the ratio of the open circuit voltage at your terminals divided by the short circuit current. So if you shorted the Thevenin equivalent network here, if you short the terminals and get the short circuit current flowing, and you open the terminals and get the open circuit voltage, by ratioing those you get what the Thevenin impedance is. Now I'm going to solve the network using a procedure called mesh currents. Here's our network. We have our unknown little I in the bridge resistor and cap I, the current coming out of the voltage source. Never mind this recipe here. I'll talk about that in a little bit. Now what we do with mesh currents is we write an arbitrary current around each loop in the network. So I will designate the current in this loop IA, the current in this loop IB, and the current in this loop IC. It's standard procedure that we have the current circulate in the same direction in each loop. It really doesn't matter as long as you're consistent. But this just makes it a lot easier to find errors. This is a very rigid procedure that you can use for large networks. Mesh currents and make use of summing Kirchhoff's voltage law around each loop in the network. And then there's an analogous technique I'll be talking about a little later called node voltages, where you use Kirchhoff's current law to sum the currents at each node to determine the node voltages. Here we don't really care what the node voltages are, because what we're going to do is we're going to solve for currents rather than voltages. Once we have the currents, then we can determine voltages just by multiplying by the respective resistances. In an analogous manner with node voltages, you solve for voltages in the network and you can get the currents by taking voltages difference between two nodes and divided by the resistance between those nodes to get the currents. But on this one we're going to be using mesh currents. So what we do is we write Kirchhoff's voltage law around each loop, and we take it in order of IA, IB, and IC, and we'll put it in matrix form. So writing Kirchhoff's voltage law around this loop, we have IA going through 2R, so we have 2R IA minus, see, our IA is flowing in this direction, and we have a IB flowing in that direction. So we have to also take into account currents in other loops. So we have 2R times IA minus IB for the current there. Let's see here. I'm going to call these a different designator. This is going to be IC, and this is going to be IB. So this will be IA minus IC times 2R. Then the current in this resistor is IA minus IB. IA is in this direction, IB is opposite, so we have plus R times IA minus IB. And then we come in on the minus sign of the voltage source, so that's minus V, and that's going to equal to 0. All right, this is loop A. In loop B, we're going around this loop. Let's start here. We have IB is the only current flowing in this 2R, so we have 2R IB. Then IB is flowing in this resistor, and so is IA. So in this case, the positive direction is with IB. So we have R times IB minus IA. And then the current in this resistor, IB is upward, IC is downward. So we have R times IB minus IC, and there are no voltage sources, so that's equal to 0. Now in loop C, going around this loop, let's start at this resistor. IC is the only current flowing in R, so we have R times IC, and then IC is flowing in the bridge resistor, and IB is flowing against it, so we have plus R IC minus IB, and then we have IC minus IA flowing in the 2R resistor. So 2R is IC minus IA. And there are no voltage sources in this loop, so that's also equal to 0. Now, let's combine like terms. I can rewrite the equation. The top equation, we have 2IA plus 1IA, or 3IA, 3RIA. Then we have a minus R IB and a minus 2R IC, and we'll put the voltage on the right hand side. Now it's important we keep things in order, A, B, C. And you'll see why that's important in a moment. So for the second equation, writing for IA, we have a minus RIA, just one of them. Now for the B, we have a 2R, an R, and an R, so there's 4 plus 4R IB. And for IC, we just have a negative R IC, and there's no voltages sources in that loop. And for the last one, IA, we have a minus 2R IA. IB, we have a minus R. And for IC, we have 1, 2, 4 RC ICs. And that also is equal to 0. Now, I'm going to go ahead and put this using matrix notation. Just let you get the equation there, and then I'll put the I'll rewrite our equation up here. Now what I'm going to do when I write this equation, I'm going to divide through by R. So the R's will disappear on the left hand side and appear on the right hand side. So In matrix form, all I have to do is put down the coefficients. I have 3, minus 1, minus 2, minus 1, 4, minus 1, minus 2, minus 1, 4. And this is IA, IB, IC. And this is equal to V over R, 0 and 0. This is the matrix representation. So the way we read this is we have 3IA equal, or 3IA minus 1IB minus 2IC is equal to V over R. For the second row we have minus IA plus 4IB minus IC is equal to 0. So this is the matrix representation. Now when you follow this procedure, something becomes very evident. When you only have independent sources, no dependent sources in the network, your matrix, your impedance matrix, ends up being symmetric. The values on the diagonal is a sum of the resistances that the current touches as it goes around the loop. For example, for IA, if we look, we have 2R plus R is 3R, so we have 3 of them. For IB, we have 2R plus R or 4 R's. And for RC, we have R plus 2R or 4 of them. So the diagonals are the sum of the resistances that the loop current touches as it goes around the loop. And the off diagonals are symmetric. If you've done everything correctly, this matrix needs to be symmetric. Minus 1, minus 1, minus 2, minus 2, minus 1, minus 1. When you don't have any dependent sources in the network. This is always the case when you follow this procedure. So it's a good, easy check on yourself to make sure that you've done everything correctly. Now, what this is here, I'm not going to go through the procedure, but you can yourself if you want to reduce this matrix. The R's stand for rows. What this means here is add minus 2, row 2 to row 3. So what I do is I multiply everything in this row by a minus 2 and add it to this row. For example, if we take minus 2 times 1, we get a positive 2. We add it to this row. This row now will have a 0 there. If I take minus 2 times 4, which gives me minus 8, and add it to minus 1, we end up with a minus 9. And a minus 2 times minus 1 is plus 2, add it to 4, and we end up with 6. So that's what that means. These are row operations, matrix row operations. And this is the recipe. And if you follow these 9 steps, this matrix will get reduced down and it will look like this. It will come down to what is called canonical form. And that's after you perform all these row operations, all these steps, this is what the matrix will look like. Well, we can pick off our currents. What this tells us now, if we look at the matrix, is that IA, 7IA plus 0IB plus 0IC is 5V over R, or 7IA equals 5V over R. On this row, 0IA, 7IB, 0IC is equal to 2V over R, or 7IB is equal to 2V over R. And lastly, 7IC is equal to 3V over R. So solving for RA, we get 5V over 7R. For IB, we get 2V over 7R. And IC, we get 3V over 7R. Now, these currents will be related to our actual network. Is if we look here, what is I? I, our little I, is IC minus IB. Well, IC is 3V over 7R, and IB is 2V over 7R. So this comes out to V over 7R. And that's the value we had before for I, and it's positive, which tells me that it's in the downward direction in the network. Now, how about cap I? Cap I is IA. Just only IA is going through the voltage source. So IA is identically equal to cap I, which is 5V over 7R. So if you wanted the other currents and other resistors, like the current in this resistor, then will be IA minus IC. Well, IA minus IC is 5 minus 3, or 2V over R, or over 7R. So that's the current here in that resistor. So that's how you use the currents. But this is a very powerful method for large networks. It's easily computer programmed because you can put it in matrix form to solve the networks for you. This next technique that I'm going to show you involves flow graphs. It's a procedure that you're not going to find published anywhere that I'm aware of. It's something I've been working on for the past few decades, and I've yet to publish it. One of these days I hope to write it up and get it published. But it's a very, very powerful technique. I've seen other people use flow graphs to try to solve network problems, but their methods are extremely cumbersome. For example, Dr. Cherry at Georgia Tech had published something in the Journal of the Audio Engineering Society many years ago, and his technique is the same technique I learned back when I was at Michigan Tech. The instructor for control theory there got me interested in solving networks using flow graphs, but the technique that most people use, like I said, is extremely cumbersome. But my technique is really slick. It leads to a unique graph. These other methods that people use that I've seen end up where they have graphs that change according to how you define your variables. The graphs are not unique, whereas mine is unique, and it is also self-checking. I've used it to solve very complicated networks quickly. It really does streamline the analysis. And I'll just show you what the graph of this would look like. If I want to solve for the voltages, say Vy and Vx at nodes Vy and Vx, I write a graph. I start with the voltage source V, and let's say we go over to Vy, and from V we can also go over to Vx, and from Vx to Vy there's a path, and from Vy to Vx there's a path. I'm not going to go through the procedure here, but the voltage gains on these paths from V to Vy is 2/5. from Vy to Vx, it's 2/5, and from Vy or Vx to Vy, it's 2/5, and from Vy to Vx, it's 1/5. These are voltage gains. That is, these are the ratio of node voltages. For example, Vx over V is 1/5. These numbers are unitless. They're gains. Volts over volts. Well, to solve this network, say for Vy, Vy over V, we just use Mason's gain formula. Mason's gain formula tells us in the numerator, we add all the products of all the gains in all paths from V to Vy. Well, we have two paths that can get to Vy. From V to Vy, we can go along this path, which is 2/5. And we add to that the gains along the other path to Vy. Well, we can go along this to Vx, and then from Vx to Vy. So along this path, the gains are 1/5 times 2/5. And then we divide by the system function, which is the system loop gain, which is just 1 minus the gains of all loops taken 1 at a time, 2 at a time, 3 at a time. We only have one loop, so it's just 2/5 times 2/5 is the loop gain. So if we multiply numerator and denominator, say through by 25, we have 2 times 5 plus 2 over 25 minus 2 times 2 is 4, or this is 12 over 21. Divide numerator and denominator by 3, we get 4 over 7. So that's Vy over V. So our Vy then is just 4/7 V if I multiply through by V. Same thing for Vx over V. Vx over V is, we take the gains in the numerator on the forward paths. So to get to Vx from V, we have this path, which is 1/5 gain, and to that we add the other path that we have to get to Vx, which is through Vy. 2/5 to Vy and 2/5 down to Vx. So it's 2/5 times 2/5. And we again divide by the system function loop gain, which is 1 minus the loop gain. And if we multiply numerator and denominator by 25, we end up with 5 plus 4 over 25 minus 4, or 9 over 21, or 3 over 7. So we see then that our node voltages, our Vx node voltage is V times 3/7, and our Vy node voltage is 4V over 7. All right, let's just check to see if these values are correct. Let's get the current I. Well, I is just the difference in node voltages across the resistor, so it will be Vy minus Vx divided by the resistance. Well, what's Vy? Vy is 4V over 7. We subtract off Vx, which is 3V over 7, and we divide by the resistance. So this is 4V minus 3V, which is V over 7R. And that's the value that we had before that we determined for I. So that's yet another method in which we could solve the network using flow graphs and Mason's gain formula. Mason's gain formula is a very, very powerful analysis technique for control systems. It's used in control systems a lot. If you don't know about it, you should look it up. Mason's gain formula. Very, very interesting concept that was developed by this individual at MIT back in the 50s. or early 60s. Last name was Mason. I don't remember his first name, but I use this a lot. This is extremely powerful.